Welcome to a new video about power electronics. In this example we will discuss the compensator design using a type 3 configuration. Type 3 and also the type 2 configurations for the compensator are frequently used in the power electronics for the closed-loop control of buck converters and also other converter types. We will see step by step how we can do that in our design, in our calculation, also verify these in MATLAB Simulink and also the TINA TI SPI simulations. So before we move on, let's first look at the theory. About the theory, I would like to discuss what the gain margin and phase margin is and what the configuration for our buck converter model is. How do we model the switch and also the modulator, error amplifier in more detail, where we have the components around it which creates this shape in the body plot. Okay, let's now look at the first part. I will discuss briefly what the frequency response analysis means. For our most important part is the phase margin. We also here see the gain margin. What this means is actually the following. We have stability margins in the control theory, which guarantees that your system is loop stable. The gain margin has the following definition or following steps. We need to find first a frequency where the loop phase is minus 180 degrees. And this frequency is called the gain margin frequency. That is actually shown here. So we see here the pink line, which is minus 180 degrees. That frequency is called the gain margin frequency. Now we need to then determine the loop gain at that gain margin frequency. So we go up in the gain plot. You see here the gain, and that gain is a part distance from the 0 dB line. So the gain margin is then the gain required to raise that part to the 0 dB line, and that is how much you have as a gain margin. If this, for example, is there, which is positive, then your gain margin will be negative. So this is the positive gain margin. In this case you will have a negative gain margin. So you need a positive gain margin in order to stay stable. The phase margin has the following steps. You find the frequency where the loop gain is 0 dB. So you start actually here at the blue line. Then you go down and you determine the phase next step between the minus 180 degrees and that phase here at that specific phase margin frequency. So that is actually the steps for the gain margin and the phase margin. But let's see that in an example, in real action. For instance, we consider the loop transfer function of this third order system. You see here 3 poles, all of them are in the left half plane, so they're stable. We can then determine now the phase margin and the gain margin using the procedures we have discussed here briefly. So we start with the phase margin first. We need to have a 0 dB. That means we need to equate the length of our loop transfer function to 1, because 1 means 0 dB. So that means we take the magnitude of this expression and then equate that to 1. That will produce, when you solve this equation, we have a 6.79 radians per second. That is now defined as the phase margin frequency. Now we need to use this frequency to determine the phase for this loop transfer function. That means the argument. So the argument of this loop transfer function at that specific frequency, which is 6.79 radians per second, is equal to, now you have 0 phase contribution by the numerator, but the denominator has minus the arctangent of omega over 4 and the minus arctangent of omega over 8, and the similar form also the minus arctangent of omega over 10. But we will use the specific omega, which is here the omega phase margin. Now when you just calculate it, you get now here minus 134 degrees. Now the distance between this minus 134 degrees and the minus 180 degrees can be calculated like so. That will give us 46 degrees as the phase margin. And this is positive, so that means this is in the part of the phase margin stable. We need to also check the gain margin. So the gain margin means that you set your argument formula from the loop transfer function equal to minus 180 degrees. That's actually done here. Now we need to solve this. And you solve this, you get here 12.33 radians per second, and that is this frequency. Okay. So how much is then the gain for that frequency, which is the gain margin frequency? Now we need to have the loop gain formula, so that we need to have the magnitude. This is the magnitude, so which is then 1000 over the square root of the omega squared plus 4 squared, and a similar form for these two. We substitute the omega GM, which is our omega gain margin. You get here 0.3307, which is in dBs minus 9.61 dB. That means we are here at minus 9.61 dB. We can go up to 0 by adding 9.61 dB. So our gain margin is positive 9.61 dB. So you're looking at the values, that means that this system is loop stable. Let's check that in the MATLAB. So this is the Bode plot you can generate in MATLAB using this script. So you define the Laplace parameter. This is the loop transfer function shown here in S. And then you do Bode L, and then you do grid on to see also the grids. And then you determine here where your loop transfer function has a gain of 0 dB. And then you look at the phase associated with that, that is then 46. And you also look at the parts where you have the phases minus 108 degrees, and you go down up by the same frequency, and you see it is 9.61 dB, which is the gain margin. So both of them are correct, so we have verified our calculations. Let's also look at the controller circuits, because this is the filter and the load, which is the AC model of our buck converter. This switch here and the PWM, so the modulator, will be also modeled, and we have the error amplifier, which then measures the output voltage and compares it to the reference voltage. In the block diagrams, we are familiar with the control systems, is shown here. Here we only look at the changing values, which are the changing values are the output voltage, which will change. The duty cycle will change because the output voltage will change. And also the duty cycle times the input voltage will be then changed because of the switching. And you have our output of our error amplifier, which is then fed in the PWM generator. And the reference signal is always constant, so this is then not changing. We have two types of compensators that are most often used in power electronics. First is the type 2 compensated error amplifier, that's shown here. So the error amplifier itself is this op-amp, and the configuration around is the passive network is the compensated network. We have our reference here, so everything is then compared to this reference. So this node and that node is then compared by the op-amp, the error amplifier. And the gain of this amplifier, VC over VO, is then having this shape. We have a pole at the origin, 1 0 and 1 pole, and this is actually the shape of this gain. The type 3 compensated error amplifier is similar to that one. We only have two components in addition. So you see here the R3 and a C3. And now the Bode plot looks like so. Again, a pole at the origin, 1 0 here, another 0 here, and 1 pole here, another pole here. So in total 2 zeros and 3 poles. And the transfer function for the first case, for type 2 compensated error amplifier, is shown here. You see the pole at the origin, 1 0 and 1 pole. And this is the expression for the type 3. Most of the time you can use type 2, but it can happen that you need or require more phase contribution by your error amplifier, so then you need to go to the type 3 compensated error amplifier. Şimdi. Alright, now let's see first what the expression is of our modulator. The modulator looks like so. We have a triangle which compares our control signal with a ramp signal. Ramp signal is this sawtooth, or this is the red waveform, and the control signal is controlling or comparing the ramp signal and the value from the output, and then the comparison between these two will also change the modulation voltage at the output. For instance, if your control signal is blue in this case and the red one is like so, when the blue one is above the red one, that means we have a high signal, which means then that this is the VO, the V modulation is Şimdi. So next part is about the modulator. First start with the PWM modulator. This is a triangle we can use as the modulator model. We have the ramp signal, which is going like so, which is our sawtooth, which has some specific amplitude, and we have our control signal. Now, depending on the output, the control signal will change. It will be staying here or there. So that will also change the duty cycle. You can see the duty cycle is like so here, let's say 20%. And when we require more output voltage, then the control signal will go up and create a larger duty cycle. So in order to also transfer more energy to the output. So the modulator average output voltage can be calculated using the formula we know in a general form. So we have now the integration from 0 to t, so full period of the changing modulation output voltage. And this will result then in this form because we have only from 0 to t on, which is our on time. And in that time, the signal will be just Vs, which is our input voltage. But the modulator transfer function is what we need. That is the change in the modulation output voltage divided by the change in the control voltage, because the change in the ramp voltage is constant. So the only change in the control voltage is important. And that is then also defined in this derivative form. We can also write it like so. And then you can see that the control voltage here and the control voltage there will cancel each other out. And that will result in Vs, which is our input voltage, over the ramp voltage, which is shown here in red. And this is now a constant we can use, and this is also what you can get from the IC, which makes this error amplifier control, so you can find that also in your IC. The next part in our circuit is the filter and load. That is shown here. This is the model of the buck converter, inductor and the capacitor, having the equivalent series resistor. And we have the load here, so altogether we need to have a transfer function. And that is given by the F, which is then the output voltage over the diode voltage here. And that is then using circuit analysis, we will come up to this expression, which is a second order transfer function. Now this is given in the Laplace domain S. That's also here, this is by the way a constant, so the modulator is not frequency dependent. The compensator itself has the following transfer function, because that can be determined by looking at the output of the compensator divided by the input here, which is the VO. Again, changing parts. It's all in Laplace domain, so that will be then the open loop transfer function of our error amplifier divided by 1 plus the open loop transfer function times the beta, which is the compensated network around the error amplifier. But the error amplifier open loop transfer function is given by this expression. You see here the DC voltage gain, which is a first order model, by the way. You see here the pole at the omega PE, and when you substitute this in here, you can get a more complex expression where you have also an additional pole. But most of the time, the loop gain from here, which is then the open loop transfer function of the error amplifier, and also the beta altogether is much larger than 1. That means this is much larger than 1. So we can approximate this expression by this, and then you have here the open loop transfer function will cancel each other out. Then you will have your expression for your compensator design will be then 1 over the beta. And the feedback transfer function or feedback element is the beta. Now let's see now the calculations for our example here. We have here our DC-DC buck converter with an input of 60 volts, and we need an average output voltage of 15 volts. The current must be 2 amps. We also have designed for a peak maximum peak output voltage ripple of 1% or 0.01. We have done this in the previous examples, and then we came up to these values. Also after fine tuning, we have increased our capacitor to 20 microfarad. Here we will use the equivalent series resistor of our capacitor 0.4 ohms, for inductor 0.025 ohms. Our load must be then 7.5 ohms minimum in order to have also a maximum current of 2 amps. And we have here selected a switching frequency of 100 kilohertz in this case. And now the design objective is design a type 3 compensated error amplifier for a stable loop control system. And we also need to design for a crossover frequency, which is then 10 times smaller than the switching frequency. So in this case, it's 10 kilohertz. And there is a phase margin of 55 degrees required. You see here again the circuit we have seen before. Now when you make this more detailed, you see here again the switch and the filter and load. But now the error amplifier has also this beta, which is our compensated network here. In addition, we need to compare this reference signal here with this inverting input, which is coming from the output, and that needs to be also generated using this voltage division, which is then for R1 and R4. This PWM generator, so the modulator, will be then like so. So there is an input at the inverting input, which is then this ramp going up and down, and we have our error output voltage from our compensator network and also the error amplifier, which is then compared with that ramp signal. Now that will then generate a signal which then changes the duty cycle by activating this driver and also the switch. First we'll look at the filter and load transfer function that's already given here. We first transform that in the j omega domain that's shown here, because we need the gain and also the phases later. Now the modulator transfer function is already given, which is not frequency dependent. It's given here in Laplace domain just for completeness, but it is really a constant, which is then Vs input voltage over the ramp voltage peak. Now this is a value which is in most ICs, so which has this error amplifier and also the other parts like the PWM generator. This is a constant, or depending on the values outside the chip. Now the type 3 compensated error amplifier transfer function is given by this. You see here the minus sign because there's an inversion here, so it is sort of an inverting amplifier. There is also here this part which is a constant. There is a pole at the origin, pole here, there is another pole, so 3 poles and 2 zeros. Okay, now most of the time it is perfectly valid to assume that R1 is much larger than R3. That means this one is much larger than this one, and the C2 is much larger than C1. So C2 here is much larger than C1. Then what happens? Then this transfer function then can be approximated by this, which is still a third order transfer function, but it is easier to calculate values. Why? Because you see here now directly each zero in each pole, which is now depending only on 1 or 2 components. And here you see also the resistor R1 and R3 together. But we will see later that we will use double zero and double pole here as our design procedure, and there's also a pole at the origin. Loop transfer function. Loop transfer function is given by the modulator transfer function times the filter and load transfer function times the compensated error amplifier transfer function. So all together. And that is then given by Vs over the Vramp times the transfer function for the filter and load, and times this, which is our compensated error amplifier approximated. And that is then given here in the j omega domain. You see here actually this is quite a complicated expression, but we will see how we can massage this and then divide it in smaller parts. Okay, let's bring it there. First look at the phase of this loop transfer function. So the argument of this loop transfer function is the argument of the modulator transfer function plus the argument of the filter and load plus the argument of the compensated error amplifier. So there are 3 parts, but we know that the argument of the modulator is 0 because it is frequency independent. So there are no frequency dependent components in it. The the filter and the load transfer function does depend on, of course, on the frequency, because there are inductors and capacitors there. And that is then given by this expression. You see here that the arctangent of the, because of this 0, so it is positive, there is also minus the arctangent of this part, which is in the denominator, but there is also an additional 180 degrees. This happens because the expression here in the arctangent, so the fraction here is negative. So you will be then in the third quadrant, so you need to add the 180 degrees also in order to get the correct phase. Now, we know that our crossover frequency is 10 kilohertz, so that means the omega here will be then 2 pi times the 10 to the power 4 hertz. And also we know the inductor, the capacitor and the resistor and all the other parameters, so we can just evaluate this. So let's do that. That's all shown here, so everything is substituted. You see here omega t, so it is evaluated at this crossover frequency. It will give you minus 146 degrees. Now the phase margin is then equal to the 180 degrees plus the argument, so the phase contribution of the loop transfer function at that frequency, which is the crossover frequency. So in order to know what then the argument of that loop transfer function must be, we need to do then the phase margin minus 180 degrees. That's actually shown here. So we know the phase margin must be 55, so that means we need to have minus 125 as our phase of the loop transfer function at that specific frequency. Now, that means the following. This is then minus 125 degrees. This is 0. This is already minus 146 degrees. So how much must be then this argument of the G3, which is our compensator? And that can be then calculated here, which is then 21 degrees. So we can say the argument of G3 must be 21 degrees. But we know that because of this inversion, we get a phase shift of 180 degrees, so minus 180 degrees. So we need to compensate for that. That means we need to have 21 degrees, but we also know that we have or need addition also 180 degrees. So the compensated amplifier or compensation will be 21 plus 180 degrees, because in order to compensate for this minus 180 degrees, you get now 201 degrees, which needs to be provided by the compensator itself. The magnitude of the loop transfer function is given by the product of the amplitudes or the magnitudes of the three parts. So the loop gain must be unity at that crossover frequency in order to also have the definition for the phase margin correct. We know what the expression for the magnitude of the filter load is. That's actually shown here. So when you now substitute here the value for the components and also evaluate this at omega t, which is then 2 pi times this 10 kilohertz, you will get here 0.04636, which is then in dB is minus 26.7 dB approximately. Now the modulator gain, this is 15 or 23.52 dB for this IC, which is then LM5146, which is a DC-DC buck controller IC, which has this error amplifier, the PWM generator, and also other components parts in order to create this loop for our buck converter design. This can be a different value, so if you take another one, this can be 20 or 10 or depending on the components or settings outside the IC. But at the crossover frequency, the compensator now needs to provide a gain in order to have a gain of 1. So we need to have a gain of, at that specific frequency, of 1.438. So how do we calculate that? We know that the product of the G3, M and F, the amplitudes, must be 1. We know the M and also the F at that specific frequency, but we don't know this yet. Now, in order to calculate that, we look at the 15 here for the M, and for the F we know that it's 0.04636, so that means 1.438. This is how much gain we require from our compensator. Okay, let's bring here the values we have determined, the compensator phase we need to provide, and also the gain of that compensator at that specific frequency, which is our crossover frequency. Now, if we now look at a DC-DC buck controller IC, which is LM5146, that is this chip. You can see also here some more details and also about the pinning. You see here the compensator input, which is also the feedback, and also the values, the components here, which then needs to be connected here, which are the C1, C2, C3, and also the other resistors, in order to create that loop for our control. Now, when we look at the datasheet, we see some imported parameters. This is now the summary of the most important parameters for this IC. You see here the input voltage range, the maximum current, the control mode, which is in this case voltage mode. We also see here that there is our reference voltage of 0.8 volts, so that means this is always 0.8 volts, so it will be compared to the voltage there and then will produce some error. There is also a ramp amplitude, which needs to be here 4 volts. Why? Because the gain is 15, so this is then KFF, means forward gain of this PWM generator. There's also an error amplifier in it, which has an open loop DC voltage gain of 94 dB, or in scaling values, which is then 50,118. Gain bandwidth product of 6.5 megahertz. Now, assuming, which is in this case a first order model, we can calculate the pole of the compensator by doing a gain bandwidth product over the open loop DC voltage gain, which will give you approximately 130 hertz. Now, this is from the datasheet of this buck controller IC. You see some imported parameters here. First one is the PWM feed-forward gain, which is indeed 15, as we have calculated or used here. From the error amplifier, we see that there's an error or a reference voltage of 800 millivolts. The DC voltage gain, open loop DC voltage gain, is 94 dB, which is then, in this case, 50,118 volts per volt. And also the gain band product, or unit gain bandwidth, is given as 6.5 megahertz. And assuming it's a first order model, we can then calculate from there the compensating pole using this formula. Okay, the next step is using our method to calculate the compensator values, which is the K-factor method. Now the compensator will be used having a double zero and a double pole, as shown here. So our transfer function is adjusted. We still have a pole at the origin, so 3 poles and 2 zeros. So we need to determine now, and also use this as our transfer function to get the compensator values here. The first step is calculate the factor, which is the K factor. Now K is given by this expression, which is the square of a tangent of the compensator phase contribution plus 90 degrees over 4. We know how much phase we need to provide by our compensator, which is 201. When you now substitute that here, we get a value of 10.4, which is actually close to 10.37, so this is now rounded off. Now the next step is calculate the resistor value R2. That can be done by first taking one of the values for the resistor, because we have 4 resistors, so assuming or letting R1 is 200 kilo ohms, we can calculate R2 using this formula. We see here R1 and also the magnitude of that compensator, that crossover frequency, and also the K factor, so we can just substitute here the values we have. We get here 89.18 kilo ohms. Step 3 is calculate the capacitor C1. That's done using this formula. You see again the crossover frequency, the resistor R2, and also the square root of K. Now when you do the calculation here, you get here now 55.34 picofarads. The next step is calculation of the capacitor C2. For that we use this formula, and that will result in 575.5 picofarads. The capacitor C3 is calculated using this formula, and there we will use again the value of K and omega T and R1 in this case, and it will give us 256.6 picofarads. The next step, step 6, is the calculation of the resistor R3, and that will be done using this formula, and that will give us now 90.23 kilo ohm. And we have also step 7, which will then calculate the final resistor R4. That needs to be calculated looking at the reference and also the output voltage. Now, if I look at this, in order to compare the reference voltage with this inverting node, that means we need to have a voltage division of R4 over R1 plus R4 times the VO, which is then the VREF. So here you can use the expression to calculate now the R4, because we know what VREF is, we know what VO is, we also know what R1 is because it's selected in step 2. So we rewrite this, so cross multiplication, you get this expression. Now collect all the terms with R4 together on the right side. We have now this expression. Now we can equate now the R4 here, and that will be then, just substitute the values here, will result in 11.27 kilo ohms. Now let's now look at the simulation results in MATLAB Simulink. In this case we only use MATLAB. These are the values we have calculated and also selected one. So these are the results from the selection. Now we'll see here that we also have the parameters from our error amplifier IC. Now this is the script I have written for our simulations in MATLAB. You see here again the definition of the Laplace parameter, the specifications for our buck converter, the switching frequency selection, also the other parameters here. Now when you now look at the loop transfer functions, now the Bode plot for the loop transfer functions are shown here. You see the F, which is the filter only, the blue line. Multiplied by the modulator, the filter multiplied by the modulator is shown by this orange line. So it's actually shifted up because there is some gain, only no phase or reactive components in it. This yellow line is our compensator, that is actually given by this, and this purple line, which is our final loop transfer function. You see here now that at this 10 kilohertz, because that was our crossover frequency, that the gain is not exactly 0 dB. It's close, it's minus 0.0, let's say 28 dB, but it's not exactly 0. So there is a small error. That is not a problem. Now for the loop transfer function, you see at this phase, at the same frequency, we have a phase of minus 122 degrees. And the compensator, according to MATLAB plot, we have here a 24 degrees contribution. We know that the negative phase contribution will be not added by the MATLAB script, so we had here before 21 and we added 180 degrees. So this is now 24 instead of 21, so we actually have more phase contribution by the compensator. Now altogether, looking at this phase of the loop transfer function at this 10 kilohertz, which is also the 10 kilohertz here, which is almost 0 dB, we can say that the phase margin is, now in order to calculate that, you only need to calculate the distance between this one on the minus 180 degrees, so we get 58 degrees, which is now sufficient because we want to have 55 degrees, so this is fine. We can now look at the simulation results in Tina TI Spice. And for that, we need to first have the simulator circuit. This is the circuit. You see here, let's start here. This is the part where the buck converter is modeled. You see here the equivalent series resistor of the inductor itself, the equivalent series resistor of the capacitor, and the capacitor value itself, the load. This is the modulator, which is 15 here as the voltage controlled voltage source. This part here in total, and this is the compensator itself. This is the error amplifier, which is the DC voltage gain. These two are compensated, and the C compensator will create that pole at the 130 hertz approximately because of this gain boundary product. This minus 1 is just to make this inversion, and that will be then put here in between here, and there is a C1 here, C2, R2, R1, R4, and C3 and R3, and the values are shown here. Now this is again determined from the parameters from the buck controller IC, again we have discussed before. Now let's now look at the loop transfer functions. You see here first, actually the blue line is our loop transfer function. The pink one is our compensator transfer function, loop transfer function. The green one is only the filter, and the dark brown one is our filter and the modulator together, so the product. Now looking at only the loop transfer function, you see here the crossover frequency is 9.95 kilohertz, so small error. And when you look at the compensator here, it has indeed 203 degrees at the 10 kilohertz. And also we see that the loop transfer function has a phase of 57 degrees at the 10 kilohertz. So this is all fine, and you see that this is different than in the MATLAB, that this is also the phase margin, almost the phase margin, because the phase margin frequency is a little bit smaller than the 10 kilohertz. So we have here now a phase margin of 57.1 degrees. And again, as said before, the compensator will now produce or provide 203 degrees. So the phase margin here is now 57.1 degrees according to the calculations from Tina TI Spice. So this is in agreement with our checks and simulations in MATLAB. Alright, we have discussed how we can design a type 3 compensated error amplifier using the K-factor method for our buck converter. We have used the loop transfer functions and also determined how much phase contribution our compensator needed in order to get a specific phase margin at that specific crossover frequency. If you have any questions, comments about this example, please let me know and I will try to answer them as soon as possible. See you next time in another video. Take care.